Hello everyone, welcome back. So let's jump into some problems, some example problems. But before we do that, we'll talk about how you can actually solve these problems. It's not too difficult. You more or less follow the same tips we always have. But it's a little bit different now that we have a new equation, so let's talk about it. So first thing you do, get that x, y, z coordinate system going. Where is your origin going to be? What's going to be the positive x, y, and z directions? Okay, figure it out. Second, draw the particle's free body diagram and establish the direction of the particle's initial and final velocities. You got a particle, what direction is it going, or is it going at the end? Make sure you know what those directions are. Then resolve your force and velocity, or impulse, momentum, whatever you have, into x, y, and z components and apply that equation we just got using its scalar form. Finally, solve. Also, if the forces are functions of time, then you have to integrate them. Otherwise, you can just use force times the change in time. Sometimes we'll be giving a diagram for the force. In that case, it's just the area underneath the line. Love graphical solutions, always nice. Now let's look at that example. So what do we have here? Well, we have a ball. It's a 0.5 kilogram ball, and it strikes the rough ground and then it rebounds. It says, neglect the ball's weight during the time it impacts the ground. Okay, so we've got to figure this out. So let's try it. Let's see if we can use our linear impulse and momentum equations to solve this. Now I'll do this one with you, but the next question you have to do on your own, so be prepared for that. Okay, I say that, but it's a video. You can always just fast forward and see the answer, but you know what I mean. So what we want to know in this case is the magnitude of impulsive force exerted on the ball. How are we going to do it? Well, first we're going to get our momentum and impulse diagrams for that ball. And then we're going to apply the principle of impulse and momentum to determine the impulsive force. Okay, first let's get our diagrams. So we have our ball. Here's mv2, here's mv1, and we have these three forces acting on it. Now, as a note, I know this is drawn at an angle, and the angle is like, oh wow, look, it matches. That's not 100% correct. This is just the component of the normal force that's not coming from the weight. This is the impulsive component. The normal force is just blocking out the weight, more or less, and it's blocking out, it's also applying an impulse to this ball. And so we're just kind of breaking it up into two components. So we'll just say like normal full is equal to the normal force plus F. And both of those will be pointing straight up. It just don't have them overlapping. We want to make sure that you understood that the normal force due just to the weight doesn't do anything. Okay, that's because they act in equal and opposite directions. So we've done that. And now we know that this force is what has changed its momentum. Now, interestingly enough, its linear momentum in the x direction should have been constant. Only momentum in the y direction should have changed. So we get something like this. If we want to, we can do this as a vector form, or we can do it as a scalar form. In this case, we'll do it as a vector form. And we look at all our values here. We have the mass out front, and then we break the force, or say we break the velocity into components. So it's 25 cosine of 45 I. It's positive because it's going in the positive x direction, but it's negative because the second component is negative because it's going down. In the second case, we still have a positive x velocity and now a positive j velocity. So therefore, the impulsive force vector is going to be 4.509 I plus 11.34 j. So I did misspeak earlier. It does have a an x component because that has changed apparently. So must be friction or something else causing that. But still cool. Still cool. Okay. So with that in mind, we are able to solve. We solve for this, we solve for the impulse, and we can break it into components. And we're done. Now, here's one thing that's going to be confusing for all of you. When I say impulsive force vector, I am not asking you to say, okay, what is that force right there, break it into components. Because I didn't actually give you a time in this thing. It's a weird thing. You'll see this said a lot in problems, but when it says impulsive force, it's asking for I. It's asking for the impulse, which is technically not a force because it's Newton seconds. It's force times time. But you're going to see that, so just be prepared for it. And finally, the magnitude I would be this. So, take each component, square it, add them together, and then take the square root. So that's 12.2 Newton seconds. So going back here, I did misspeak when saying that this was going to be directed straight up. If it was a perfectly elastic collision, it would have been straight up. That would be the only force here, but I'm guessing in this case, we're saying that there's some sort of friction or other force which is causing it to change its velocity. Which is fun. I like it. Okay, everyone. Thank you very much for listening. I hope this helps you, and I will see you all next time. Have an absolutely wonderful day. Goodbye.